Hi, everybody. So welcome to the final section of 4.5 Complex Zeros. I want to start with a quick reminder about end behavior. We talked about this in the first day, but I wanted to bring it back. We're going to kind of collect all of our theorems into one spot, and I have one more theorem for you, and we're going to practice finding a ton of roots. So here we go. So first thing, looking at graphs. We talked in the very first day about multiplicities of a zero, and using that to determine what's going on with our graph. So in this one, I knew it. I knew it was going to crash. I knew it. But what I do, so whenever it crashes, I have to like reset all the things. But this time I saved it for recording. So I was ready for it. Okay, so crash again. Do it. I don't even care this time. Here we go. So our multiplicities. So here we've got a 0 at 2, and our multiplicity is 2, and that tells us it's going to be a bounce. It's going to like make a U shape at 2. We also have a 0 at -3, and that is a linear, so I know it's going to shoot straight through the x-axis. Whoop. So we've got one at -3, so there's my y-axis, and then another one at 2. -3. All right, so I know I'm going to have zeros in those two places. The degree of this thing overall is 3. And we've got a leading coefficient that is positive. So I know it's going to, since it's odd, it's going to overall kind of be heading up. It's going to have kind of a shape like that. It should start very low, and it should end very high based on its degree, because it's kind of like a positive slope for linear. So at 3, before -3, I want to be below it, but I also know I want to shoot right through it. Then at 2, I know I've got to like bounce off of the graph. So let's bounce off of the graph. Then all I got to do is just connect those two ends. Whoop. So my graph kind of looks like that. Boom, graphed it, didn't even need a calculator. Let's do it again. So this one, I've got a 0 at -4. It's mult3. So I know it's going to look like this. It's going to, well, here, let me not actually draw an axis. What's going to happen when it hits the axis, it's going to kind of flatten out for a little bit and then continue on its way. It's kind of tricky to draw, but you kind of want a little flattish bit going on. For this one, we have 0 at 5, and our multiplicity is 2. So that should be another one of those bounce ones. Might be up like that, it might be down, but I don't know. Its degree is 5. So that's another odd one. So it's going to be shooting up like that. It should start low and end high. So I grab my XY axis. I've got one at 4. 1, 2, 3, 4. So that's where my blue one's going to be. And then I've got another intercept at 5. 1, 2, 3, 4, 5. Whoop. So at that blue one, I should be kind of coming up to it, and then I want to flatten out like for a little bit. So I don't want to go straight through it. I want to go through it, but kind of have a little flat bit in there. The purple one, I want to bounce off of the axis like I did before, and then just kind of connect these two in sort of a loopy-doo shape. And there we go. It's not going to look perfectly like that, but overall it should kind of have this shape of a bounce at the purple one and kind of a cubic look at the blue one. That's kind of a quick way of making your graphs and getting an idea of what the graph should look like without actually graphing anything, which is kind of neat. Okay, I want to go over some theorems that we've been talking about once this thing decides to load. We've written all these down already, so you've got a couple options. You can pause the video and write these down again so you have them all in one space, or you can go back through your notes and highlight where you wrote this on your first day of notes. This was in the 4.2 section where we talked about the real zeros theorem, saying that all 4 of these things are exactly the same. That the 0 of a polynomial is the same as an x-intercept. So here we had p of x, our p of x is x squared minus 16. So our 0 of 4, it made our whole polynomial 0. You could also say there's also x-intercepts, where it crosses the x-axis at 4. 4 is also a factor because we can divide p of x by x minus 4. So you do the opposite and we get 0. And it's also a solution because if we solve this equation for x when it's equal to 0, we get 4 as one of our answers. Should we get plus or minus 4? It's just one of them. We're guaranteed to get one of those as our answer. We wrote that in our 4.2 notes. In our 4.4 notes last time, we wrote down our wait, no, we didn't do this one. We didn't do this one yet. This one's new. Fundamental theorem of algebra. This one's very exciting. This is new. So a polynomial of degree n has n roots. Doesn't say that it has that many different roots, but it has at least n roots. You can use things like multiplicity to kind of cheat. Because if we had p of x equals x to the 7, that has 7 roots. They're all 0, but it has 7 roots. X to the 6th has 6 roots because it's degree 6. X to the 3rd has 3 roots because it's degree 3. The degree equals the number of roots. This is the complex zeros theorem. This is the other new one. So sorry, I guess there's 2 new ones. Complex zeros states that if a plus bi is a root, then a minus bi is also a root. So this is new. You got to write this one down. Really what it's trying to say is that complex roots always come in pairs. Can I kind of get out of the way a little bit? I'm going to get a little tinier. So if a polynomial is degree 3 and one of the roots is 5 and 2 plus I, 5 and another root is 2 plus I, it's got to have 2 minus I as one of its roots. We should always get pairs of these complex zeros. We should never get one of just the 2 plus I and not 2 minus I. Down here, we've got 5 plus 7i and 5 minus 7i. We've got positive I, we got negative I. We're not guaranteed 3 and negative 3. If we got 3, that's a real root. Those don't come in pairs. Imaginaries, I and negative I, 5 plus 7i, 5 minus 7i, those always come in pairs. Imaginaries come in pairs. Reals don't necessarily come in pairs. Okay? Reminder, these i's come from the square root of negative 1. Now we're going to use all these theorems in these sometimes, always, never questions. And I don't know where that went. Where did that go? You're there. These are just out of order. That's okay. We just crashed a little bit. I'm going to ask you these questions on the test of always true, always false, needs a reason, needs a theorem. Sometimes true, sometimes false, need examples. So I'm going to ask you something like this. Polynomial equation is cubic. So we got a cubic. Doesn't have to have 3 x-intercepts. That could be sometimes true, sometimes false, or it could be always true or always false. Well, if we wanted to, let's think about that. I could draw one that has 3 x-intercepts. So whoop, whoop, whoop. If I made one that was, let's see, we could say our p of x equals, let's see, x. Let's see, I kind of got like plus 2 because I kind of got like a negative 2, maybe an x minus 1, and then that last one is probably x minus 3. So there we go. There, it's true. It's true. Okay. Well, could I make a false one? Yeah, I could. Watch this. Watch this. What about p of x is just x cubed? Whoop, whoop. That one only has 1 x-intercept. So here is a false example. So that one would be sometimes true, sometimes false. It has 3 roots. Both of those have 3 roots, but there was nothing in that statement that said that the x-intercepts had to be different. They could all be the same thing. All right. How about this one? A polynomial with 2x intercepts is a quadratic equation. So it's a quadratic equation, and so wait, it's got 2x intercepts. So all it's got to do is got to touch the x-axis 2 times. Okay, can you touch the x-axis more than two? Can you touch the x-axis 2 times and not be degree 2? Is what this question is really asking. Yeah. Check it out. If I did a true example, I could do P of x equals x minus 1 and x plus 2. Whoop, whoop. So that would be like that. Oh, wrong color. Come on. There we go. So that has 2 x-intercepts. A polynomial with 2 x-intercepts, check. It's a quadratic. Yep, check. But what if, so I'm trying to think, what if I had those same intercepts and I let one of them just shoot right through like we were doing before, but then I let the other one bounce. Ooh, that would be a degree 2. That 0 would have a multiplicity of 2. Oh, but I still have the same number of x-intercepts. Well, what would that equation look like? P of x equals, so I'm going to say that one is at, let's see, that one's our negative 2 one. Just square it. So that thing has a multiplicity of 2. And then the other one just has a multiplicity of 1. Heck, I could even make the other one bounce too. So that one is also sometimes true, sometimes false. Okay, now we have a polynomial of degree 3 has no real roots. So our degree is 3 and it has no real roots. This one is finally one that is definitely false. I'm going to say this one is false because if it has no real roots, so if we are degree 3 and no real roots, we'd have 3 complex roots. But wait, according to the complex zeros theorem, according to our complex zeros theorem, complex roots come in pairs, not odd numbers. So this one has to be false. Now I'm writing this in fractured sentences. On the test, you should write full sentences. I'm saying full sentences, I'm just not writing that. Must be pairs. So a good full answer to this, repeat this as many times as you need. This one is false. A degree 3 polynomial with no real roots would have 3 complex roots. However, by the complex zeros theorem, complex roots must come in even numbered pairs. We cannot have an odd number of complex roots, so this statement must be false. Woo! Okay, let's try another one. A quartic polynomial has exactly 3 imaginary roots. You can see this one's already going to be basically the same thing. Exactly 3 imaginary roots? No. Same problem, different story. I don't care what you're saying over here. Exactly 3 imaginary roots is never going to fly, according to the complex zeros theorem. So you can say the same thing that you said before. A quartic equation or any polynomial cannot have 3 imaginary roots. complex roots, and then it just continues on from here. Cannot have three complex roots by the complex zeros theorem. Complex roots must always come in even numbered pairs, so we cannot have three imaginary roots, and the statement must be false. Woof! That's it for those. I'm going to make a separate video where I'm actually playing around with like using these things in order to find our zeros. It's going to be similar to what's going on in class. It's a cool optional video to watch, but this one's kind of already gotten its full length. So thanks for watching, and hopefully check out that bonus video as well. Bye-bye.